little few videos I'm going to link together to try and describe how this thing goes together. Videos will probably be the easiest way, and then I'll try and write instructions as much as I can as well. But the videos should describe most of what happens with one of these inverter kits that I've basically got a couple people playing with. So essentially, these are the 3 driver boards. Pretty straightforward. This is a high side. This works out to be a high side IGBT and bad IGBT, and so all these 3 are low side, all these 3 are high side, and basically what that means is this attaches to positive, all of these 3 here, and I have bus bars that I've made up to accomplish all of this. So this is the positive bus bar, and then the cap sits on top of everything. You see the caps, all this stuff has kind of been, more for the lack of better words, has been through hell because I've wrecked a few IGBTs in the process of getting this thing all sorted out. These I've decided to make the video now because I've just upgraded these to 800 amp IGBTs. I took these 600 amp IGBTs out. As you can see, one of them here. So these are still good. These ones with the thermal paste on them. Basically, I took 6 of them out and I put 8 of these back in. They're 800 amp, if that'll focus for me. And nonetheless, one thing I need to point out is the way I install my current sensors is this little corner right here. If you look, here's a factory 800 amp IGBT. If you look right here, there is just that's just smooth plastic. It's like a little circle of where I would say maybe it's from where they had the vacuum for the mold for the plastic or something like that applied. Either way, what I do is I use that as roughly a reference, and I drill that out for the digital temperature sensors, and I put one in every IGBT. And what I do is, as you can see there, that's drilled down through the plastic and into the copper, which is the bottom heatsink here. It's drilled into that copper heatsink just a little bit for a just to get the temperature sensor as close to where the heat source is as possible, and that makes everything react a lot. Makes your control over the thermal cutbacks and whatnot a lot quicker, because you have to give it a little buffer as well. So what I usually do is I have it start cutting for thermal at 70 degrees Celsius. These are rated as the numbers you saw there, 600 amps continuous at 80 degrees Celsius. So if you start the thermal cutback at 70, you're probably getting close to where inside it's probably at 80 degrees Celsius. So for that, it'll probably, that's just a kind of a guess, but it's the best we can do. I'm also pushing things to the limit. I've run 750 peak amps, which works out to be 540 RMS amps or something like that. That's pretty close to the 600 amp limit at 80 degrees, but I have it cutting, you know, at 70 degrees. So theoretically, it should have never saw the 600 amps RMS, which RMS would, technically, you should be able to run RMS amps at what the peak, at what the DC current is rated for on these IGBTs. Now, having said that, you're kind of pushing things, and sometimes you can't get that far. The leaf motor itself is approaching saturation at that point anyway, so the current is getting harder to control. And I have no traction, even with the drag slicks. It doesn't give me traction on the street. So running 750 phase amps peak is, you know, almost useless. I just have it set there so I can do good smoke shows to get the tires warm, and then I usually turn the regen knob up to limit the current down to around 700 peak phase amps, and that actually lets me get okay traction with the slicks. I still need to make sure the tires are warm and everything. So this is one of the phase out bars. I'll kind of describe all the components as we go through this. This will sit on there like that. You'll remove those 2 bolts. So you remove this far bolt here and this bolt here, and this will actually attach there, and you can see the lug I made, which is a 12 mil thread, or sorry, that's a 8 millimeter thread, and that actually attaches there and then goes through there. And what that does is it lets you attach a phase out wire on the end here. I'm going to do a few videos to kind of link these together so people understand. That's the phase bars I've made. As you can see, they're kind of fat in the middle. I've welded extra metal in there to help absorb heat and flow a bit more current, but it's more about heat because what I did was I machined this lug, I pressed it in, then I had a hole in the back, I welded up. But what happened was, because I didn't have weld on this side, it actually got a little hot, and I used to have Captain tape on here, and it started bubbling, so I actually re-cleaned these all up, and this is Clipdol, which is good for high voltage isolation. So basically I will grab the can of Clipdol, the right stuff. I used to use this stuff, it's not durable like actual Clipdol is. Here, so this is the Clipdol, that's the red stuff I painted on everything. It works pretty good. You can also, it normally comes in a can you use a brush with, but I found that the aerosol actually works really well. Then the silicone conformal coating, I've given all the boards a coating with it. I recommend making sure you have some on there, especially because between this board and this board you have full AC voltage potential. So there's a small gap there, and that's one thing I'll go over in a second is the assembly of that, making sure you have a gap there. So basically having a coating of this on the top and bottom of all the boards, silicone conformal coating, and then making sure you coat the edges of every driver board. That'll help make sure that you're isolating things on that level as well. What I usually do to mount these is basically bolt the 4 bolts to your driver board between 2 IGBTs like this, and then mark your outer holes. If you look down here, mark the holes for, just trying to make sure I can see while I'm looking through the camera, the 2 bolts, and then do the same on the other side, mark the holes for the 2 bolts, and then basically drill and tap them, and then basically pull the board off, mount the IGBTs, and drill and mark the inside holes, and then take the bolts out and drill and tap the inside holes. I use 6mm bolts. Those are going to be a little loose, which lets you have a little room to move the IGBTs around. That's not a bad idea, but make sure you get things lined up. While you're doing that, what I usually do is I pull the IGBTs tight together, this IGBT, the low and the high, tight together this way, but also when you're doing each row, try to give them a little space between each other. So I'll go over here and show you what I mean on a bare piece of aluminum that I'm actually going to build another inverter on here pretty shortly, I believe. I'm hoping to anyway, if I can get some time to do it. So I would take those 2 IGBTs, put them tight together, and you'll mount a driver board like so, and you'll put your driver board screws in there, holding it down nice and tight. Then you'll mark these outer holes, and then you'll pull this all off, drill and tap the outer holes, and then mount it. Take this off, mark your 4 inner holes, then take your IGBTs off, drill and tap the 4 inner holes, and then bolt them down. Now, before you run it, you want to put this white stuff, which is some thermal paste. There's a few different, right in front of me. Basically, I was using this stuff. Anything helps. I've had really good luck. These things into an aluminum, like this is a 1-inch piece of aluminum. Technically, I probably wouldn't even need to cool this thing once I get an enclosure done and everything, but what I'll do is I'm going to probably machine the bottom, and I'm looking at using fans like that mounted to the bottom so it's air cooled, but it'll pull the heat right away, and it should be really good. So from there, this would mount that way. So now with your next phase, what I usually do for a spacer is I put those there, and I have these little popsicle sticks there. I lay them in there like that, stood up on end, and once I have the first set mounted, I slide the second set in, and I hold them tight in the middle, but tight with that popsicle stick, and that gives you a nice little gap when you're done. You want to do something to line them up and give yourself a gap, because the next board, you don't want it to be touching by any means. You need to have a gap there. And make sure you have silicone conformal coating on all edges. Like, I mean, to spray this edge, spray this edge, spray this edge, spray this edge, and etc. top and bottom, and then clean off your spots where you run, and also mask off your little pins when you're actually spraying it. So every kit that I've been selling, I've tried to coat them with silicone conformal coating before I send them out, but either way, it's something good to do. Basically from there, that's how you would lay that out. All your driver boards go in the middle. Essentially, it'll look something like that. Then you continue. I brought my signal wires out this way. It's a little tricky because you got bus bars and everything in the way, and all those bus bars and phase wires and everything give off some noise. I use isolated signal wire, or sorry, shielded signal wires, which have a ground shield. You can see it's kind of like a stainless steel ground shield or something like that around there. And actually, I believe it's a certain type of metal that is kind of like the mu metal I have over there. Anyways, that shield at ground on this side, on the driver boards, as a rule, I've been taught to ground one side. Some people claim ground both sides, but all the people that I have taught me more about the power electronics end of it said to ground one side. So I grounded the side on the drivers, and it seemed to be pretty successful. And then these 3 wires here, or wires that are braided, there's 3 wires, one goes to each driver board. These are your 12 volt input, which I try to send a 12.8 volt regulated input. That actually gives your isolated supplies on each driver board their power. So that gives each isolated supply power to run the -5 and the positive 15 volt on and off. It actually works out to be, I believe, -5.8 and positive 16, but by the time it gets to the gate, it ends up being 14 volts after all the voltage drops through the transistors and everything. So I think that covers everything I want to mention for now. Oh, actually it doesn't. There's a couple other things I want to talk about. First off, these little jumpers here, you need to make 6 of them. Each side has them, and what they are is, if you look, this is an emitter, and I'm grabbing a spare IGBT here. If you look down there, it's connected between the emitter, and if you look right here, that's also the emitter. So what it is it's a Kelvin clamp, or a Kelvin connection, I guess you would call it, and it jumps. It's a shorter wire and as low inductance wire as you can use to go from there to there. And when you assemble it, I'll show those again in the next sections of the video. When you assemble it, that helps provide a better reference for the whole driver signal to reference. Basically the reference to turn it on, and below the reference, which is the emitter, to turn it off and hold it off. So you want to have those, and that's the same on each side. What I've done, you can see what I've done there to make that work, and those actually helped me clean up what do you want to call it, basically an overshoot more or less. It helped it control the turn off a lot better, which means you can run more power before you run into issues. So that'll cover that part, and I think I should describe all the major components of this as well. So there's the 3 driver boards. There's the brain board, which you can see here, and I've got jumpers all over it because I've done so much experimenting so far. This is a this is a buck converter from Deal Extreme for like $3, but I use it because it regulates the 12.8 volts going into the driver boards. And then this here is an Arduino with just a do-it-yourself shield on top of it. That does my desaturation detection. I have an Uno on there only because it's what I had at the time. You can use a Nano. It just needs to be something that watches the desat signals on each phase. And you see this ribbon wire here connects across to the Arduino, and it actually watches for a desat signal. When there's a desat signal, this ribbon wire gets a signal that comes back, and it turns on a little transistor down here that holds the reset button down. So that'll basically help save you from a fire, more or less. If you have a desat event for whatever reason, you need to shut the controller off. So basically, these drivers all have a desaturation detection built into them, and what they do is they try and shut the individual IGBT down if there's a problem, and then they send out a fault signal. that fault signal ends up coming back here to this ribbon wire and goes to the Arduino. If that Arduino doesn't shut it down, you'll get repeats of the overcurrent. Every 26 seconds it tries to turn back on if it doesn't get told to shut off, and it tries again, and eventually that'll cause you an issue. It'll be bouncing at the limit of the current, which my desaturation detection is, I believe, tuned to about 1300 amps where it faults, maybe 1400 amps in that area anyway. You're going to be bouncing an RMS of, you know, like maybe 1000 or 900 amps, sorry. It'll keep pulsing until something happens to get told to shut off. So usually the first fault signal ends up sending a signal to the Arduino that shuts it down. That needs to be on there for sure. And then the last thing that I have in the system, technically it's the first, is my input power, my black and red, to the whole system for 12 volts input. This is a special isolated, I believe it's isolated, but it's a power supply that can take anything from 9 to 36 volts input and gets a 15 volt regulated output no matter what. I added that to try and help isolate noise and help with issues like when I honk the horn, the controller wants to reset, things like that. I'm trying to solve that. Either way, that's a good thing to have, because if you turn on your lights and all your other loads on your car and your battery voltage starts to drop below 12 volts, you need something that bumps that back up so that first off, this buck converter always gets enough that it sends its regulated 12.8 out, so you get your drivers turning your IGBTs on full on. You don't want to give it like half voltage, and for that reason the drivers do have under voltage lockout built into them, but either way it's at like 10 volts or something stupid. So if you're turning on 12 volts instead of 16 volts like I normally do at the driver, it'll actually end up being partially on, and it will produce a lot more heat in each IGBT and they'll fail earlier. So you need to make sure you have something that sends out a 15 volt clean regulated voltage, and I'll try and provide a link for what I've ordered two of these, two different ones, but they both seem to be okay. Then I have an inductor hooked in series with it, but that doesn't seem to help, so I'm going to be removing that soon. And then yeah, that's my that's my buck converter that feeds these two wires here that go into my drivers, and then this here on the brain I have regulators, linear voltage regulators that are set. One is set to give the brain like 5.4 volts. You want to keep it a little above 5, because once there's a bunch of loads on it and stuff, you want to make sure it stays above 5, or else it's more prone to brownouts. And then this one gives a regulated 10 volt out, which goes to, actually it's regulated like 12 or something like that, but it goes to another isolated supply that's under this ribbon cable here. And that isolated supply then feeds power to the current sensors, which need 10 volts in. Then they come with their signal out through a 2-to-1 voltage divider and sends a 0 to 5 volt signal back to the brain, so it knows what the current is. And those should be roughly 2.5 volts at the brain, measured on the brain legs when everything's powered up. That's neutral with no current flowing, so that's something else we've got to keep checking on. What I'm going to do is, as I assemble this, I'll make a few short videos to add to this video, and then I will also bring in my oscilloscope to measure pulses, and I'll show you how to watch for the desaturation events, and I'll show you how I usually test to make sure the Arduino works to catch a desat as well. And I program my Arduino with some simple code that just flashes 1, 2, or 3 flashes to let you know which phase is out. You can do all kinds of things with that, but it doesn't need to be anything fancy. In fact, you almost don't even need an Arduino. You just need something that does some sort of a latch up event to shut the brain off. But Arduino's easy, and it's cheap, so works. The second part to the video of the assembly of my inverter kit that I've been basically putting together. Now this is in a leaf housing. I'll point it out too. It was not the right way to go. I went through hell to well, I had to drill new holes and tap new holes, and all the center holes for all the center parts of the center row of holes for both sides, the high and low IGBTs, went into the cooling jacket. So we just spent probably over 20 hours welding those up, which was really tricky. Basically built up a little weld and then drilled and tapped it, and then basically had some leaks, had some cracks, had to deal with all that stuff. And kept going from there. got it all sealed, did some pressure testing. I also run my rad cap as a 0 psi rad cap because the cooling system only runs around 30 degrees Celsius when it's about 15 to 20 degrees above ambient as a rule of thumb. So basically the coolant doesn't get warm. You don't need pressure on it. So I keep the rad cap at low pressure, basically 0 psi rad cap. As you can see here, these are the negative phase links here. This one and this one here. This one here. These all come from the cap. I'm going to kind of show this as I can think of it to go through it. This here, these 3 lugs are for the positive. So basically, this cap here is the OEM leaf cap. And the OEM leaf cap is really good. It's a badass cap. There's the specs on it. But basically, it's about the equivalent, I would say, maybe to 2 of those power ring caps. They're really good power ring caps. It's amazing. All these joined together by going like this, and it's poly, so it doesn't matter if you go positive or negative or positive, it doesn't matter which way you hook it up. Having said that, the way I have it set is this is my positive on here, 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 and then the negatives are here, here, and here. And what I use is I have a negative bus bar that comes across. So basically you want the power coming from, if you look at this bus bar, a negative phase wire connects there, or sorry, negative battery wire connects there, and a negative positive battery wire connects to that one. The way that works is it bolts on like that. I've built up, you can actually see, I welded and built up the top of this to flow a little more current. I added a little more here because the plan is to run up to peaks of 750 amps DC. So I want to run that through, and I wouldn't call this a continuously rated 750 amp DC bus. Anytime you get some exposed aluminum or copper or anything, definitely spray some more Clipdol on it. Make sure it's all isolated really well. You don't want to get any problems with things arcing or whatever inside. In fact, the reason those are like that is I actually had an arc happen at one time when I believe I blew an IGBT. Long story, but had a bad solder joint on one of my isolated power supplies that holds one of the IGBTs off. That didn't hold it off properly. It basically turned on or whatever, and another adjacent IGBT tried to pulse its power. The desaturation detection didn't. It did its thing, but unfortunately something happened where they both turned on. I think one failed shorted, and then the other one adjacent was not turning off, and they basically popped my cap and it started arcing inside. It arced actually across from here to here. It arced on a bunch of these and burnt 3 of the legs off my cap. I actually bent up some copper, dug out the potting here, and I re-welded them with my TIG welder. That was a pretty sketchy thing, but I grounded right to the lug so that the current was flowing right through there. And then basically I cycled power into them, starting at 12 volts and working my way up back to 400 something volts to make sure all the legs of the cap worked. And then I measured the capacity, and the capacity is still good as new, so I'm in luck with that. It's been running for 3 months like that, so I have no fear in running that cap. I do have a spare leaf inverter that's full, another one full of salt water, so I have another cap I can use down the road. Anyways, to continue, so this is the positive bus bar. You can see how it links together. It joins to all the positive side IGBTs. These are the negatives that jump across. You can see how I left a nice big gap there, and I did rounded edges. Make sure all your edges are round everywhere. Like even here, this edge of this phase bus is rounded, and then coat it. The Clipdol that I showed you earlier is really good stuff to coat them with. This one I tried painting it on with a brush. It doesn't work as good. I'd prefer to spray it with aerosol, so I like the aerosol. Make sure you sand and scuff them and clean them with alcohol or something really good first, and then mask the areas that you want it to flow current. Now another thing to use while I assemble it is this, grab this right here. Whoa. This is probably the world's best dielectric grease. This is pure silicone. If you get this stuff, do not get it, like make sure you clean it off everything when you're done, because it is super slippery and nothing will ever stick to it after you apply it. So I apply that to all these connections for 2 reasons. Number one is you need basically another trick to mention. You need to scuff that aluminum, and then you need to apply the compound 70 or some sort of dielectric grease immediately, because that's going to stop air and oxygen from oxidizing that aluminum surface. So all of the aluminum surfaces that are exposed get a little smear of compound 70. And then on top of that, when you have copper that bolts to aluminum or vice versa, like these clamps, these from here are aluminum, which go to the copper lugs on the cap. These three are actually bare copper, because these two anyway are bare copper, because I had to weld on new pieces. So I put a little CP70 on there, because you don't want to create what's called galvanic corrosion. And what will happen is when you have two different metals with electricity flowing through them, it creates corrosion. So what you do is you put some CP70 on there, or dielectric grease of some sort, but CP70 seems to be the best, and it's highly recommended by Luke and a few others. You put that on there and that helps stop the corrosion. These are hooked up for my phase out. So these are how I run the phase out. So you can see how it comes from the phase bus bar, goes through the current sensor on the lug that I made, that I showed earlier, and then comes through a wire. Now, in the future, my plan is to build a bus bar here and do laminated bus bar. This is part of the OEM Leaf phase bus bar setup. It's a nickel-plated copper. What I've done is I've potted over the ends, I've cut it off and potted over the ends that are exposed. And what I do is I use this to create a support, a stress relief on these three wires, and then these connect up to the actual car lug right here. So these are what the three phase wires. Sorry, I got a piece of tape in the way. Little note for myself anyway. These connect up to those other three inside. So basically you can see how this would normally go on there and a bolt like that. What I have is this thing creates the stress relief and supports things from inside the inverter, and it goes, I've flipped it around to go this way, I believe. And then basically those other wires come up through the bottom, through this hole you can see down there. They reach up and come from the bottom. My positive and negative comes in through here. It's also a sealed plug. I think that's everything. The other last thing I need to point out probably before I go to the next section of the video is this right here is the OEM bleed resistor. It's a giant, I think it's 64,000 ohm ballast resistor. What this does is it hooks the positive and negative on the cap. Right here and here I just hook it up like this when I'm putting the cap on. And what that does is it, when you shut the ignition off and both your contactors open, it starts to bleed the voltage down on the capacitor. As you can see here on the capacitor, I even made myself a note to check cap voltage before working on it and replace the bleed resistor, because I've actually had a couple issues with the wires on the bleed resistor where they got weakened. So I've actually potted them for some stress relief and they're okay for now, but in the future I'm going to actually be replacing this. So I think what I'm going to do soon is start a whole second inverter build. I'm going to get this back in the car running with the 800 amp IGBTs, continue testing that route, and then I'll start building the mechanical part of the second inverter. I want to have a spare inverter for when I go run the quarter mile with this thing, because it's over in the mainland. I got to drive over there, got to charge, got to do all that stuff. And not only that, I want to push the limits to the max, so you never know what will happen when you do that. With the slicks on the track, I'll have pretty good traction, so I'll be turning the current up pretty high. So we'll see. I think 750 amps, phase amps, peak, won't probably break loose very easy over there, but I bet you around 8 to 850 peak phase amps probably at the track will be able to break loose. So I'll have to find the sweet spot where it, lets me break loose a little bit, and then I'll try and do what I can to get traction or something like that. Anyway, basically now I've got, I just went home and grabbed my 2-channel scope, threw it in my backpack, brought it in just so I can show you how to scope all the gate signals before you hook up any power. So right now, this is the positive DC bus in, and the main capacitor. They're not in there, they're not hooked up. The battery's turned off on the car itself, and I have a main disconnect that it's a second, like it's a third level of safety in the middle of the battery pack. So when I disconnect it, it splits the battery pack into 2 separate 235 volt sections, and then on each output side of the battery there's a contactor as well. So that's the main disconnect is disconnected as a level of safety for me to work on the car, And then also the key for the ignition is in my pocket right now. So the ignition's off, contactors are all disabled, and this is disconnected, so we don't have any voltage we got to worry about. All I'm trying to do is I've hooked up just a little 4S LiPo pack to my input voltage for the brain system. So the brain, the voltage regulator, that DC to DC that I showed you, that can take anything from 9 to 36 volts input and spits out 15 volts at all time. That's in there. The voltage regulator, the brain, and the Arduino to watch for desaturation detection. That's all inside underneath this cover here. So I've got it flipped over just so I can work, test all the gate signals. So now I'm going to go through that. While I do that, I'll show you a program that we use for setting these up. All you use is this. I've downloaded Realterm. It was suggested by Lebowski. It works pretty good. You run a USB cable to a USB to serial adapter, and then that goes right into connects to the brain. So the next step here is you set it up with 115,200 baud, and then basically you just have to pick whichever serial port you have, and then you open it or click change. I think either one works. And then you set it up like this, and I always select the rows. This is how big of a thing that makes the screen a little bigger so you can see it easier. Then another thing I like to do is click scroll back, just so you can actually scroll the slider here on the side up and down, and lets you actually review past things. And sometimes I'll even set that to 2000 instead of 200. So now I've already set the brain up in the reset or setup mode, so it should bring up the information. So now we already have the menu. This has already been programmed. I've already gone through that. That's in another video. I'm going to just bring up the PWM setup here. You can see all the information's already in there. And what I'm going to do is I'm going to go to F, and then I'm going to click enter. And now you can actually hear, because I'm running 6 kilohertz PWM, there's a couple tricks to this. You can actually just take your probe and you can actually measure with one end. Now this isn't a super clean signal doing it this way. You should hook up the ground, but I'll just show you what that does. And it lets you see a floating signal. It looks a little funny. It's not the end of the world. I'm going to set the trigger up before I forget. The trigger I'm going to do is just to show how this should be done. I'm going to hook up the ground clip to the emitter like you're supposed to. And then it'll make the signal look a little better. So just get that in there like that. It's a bit of a son of a bitch to get in there. And we'll set this right there. Now that's what the signal should look like. So while I'm here, what I'm actually going to do is I'm going to disconnect my desaturation wire there. On all the high sides, you got to run. This is something I need to mention as well. I'm going to move the probe out of the way here. On the high sides, you got to run this wire that comes from that corner of the driver board down where my finger is, in front of my fingernail. Try and get in there really good. That wire comes up and it goes to the positive bus bar. What it is it goes to the collector side of the IGBT, which is the outside, as you can see here. These two, I've actually got them routed underneath. They actually go underneath the bus bar, but they still go underneath the bolt that's down here, which is, looking at it from right there, you can see my finger just touching the bolt. And that's a collector. That's the outside of the IGBT. Here's the last one. You can probably see the bolt down here a little easier. It's like straight below my finger there. This wire comes in, it actually has a ring terminal like that, but it's actually underneath. I've started using it this way because it allows you to switch one IGBT at a time without pulling all those bolts out. It lets me do different things. I've been through a few repairs with this inverter, so there's a few reasons for that. So before I go any further, I'm just going to double check all the low side gates just by letting it float again. That one looks okay, 2 looks good, middle phase, and then this is the final phase. And that looks good. So all my gates look good. If you have a blown IGBT, it's not going to look the same. I'm just going to hook this ground clip up again just to show you a little bit of a screenshot here. So that's what it normally looks like. I'm going to push the stop button so we can just freeze that. So now I've got that froze, and I don't mind letting the PWM mode, just run on for a while. That's another little test that doesn't hurt to do. And then I take my thermal imaging camera and I just go over the board quickly and see if I look for any hot spots. If you got a isolated power supply or one of your gate drivers or something getting hot, like, you know, above 60-70 degrees when it's like 15 degrees ambient temperature, you've got something probably going on. You want to inspect all the hot spots. Everything right now is running, you know, if I was to get my thermal camera out, it'd probably be around 30 degrees max at any given point on that circuit board. So looking at this, the gate's nice and clean. Now this is my older scope. I have a newer one that has 4 channels. It gives you a way cleaner trace, but I didn't really need it because I just want to verify I had signal PWM at all the gates before I hook up my main battery pack and try running the car again here in about an hour. Nonetheless, you can see a nice round slope, and then it slowly gains. So if we're to put, we'll move this out of the way so we can see it better. If we're to put the cursor here at the very top, we'll even zoom it in one notch. We'll bring it down like that. Then we'll move the cursor. The very top, something like that, looks to be about 14 volts. That's at the end of a long PWM period. At the very start here is where it's initially, like, we'll call it full on more or less. It's only down to 12.6 volts. What that is the gate slowly charges a little more every cycle. This is at a 50% duty cycle, so if you look at this, you should see an equal on time to an equal off time, and that's set up here in the menu as well. You want to make sure that's set at 50% duty cycle. If you see something different than that, there's going to be an issue, so I'm going to go through that here in a second. I'm going to test 2 different features in the next section of this video. One last thing to check is there is where basically 0 volts is, where you can see your scope trace start point. And look at this, that's the off. So that means it's turning off with this much voltage, which is about right there, 5.6 volts. So like I said, I'm actually feeding about 16 volts into the circuit through these wires. They go to, it's not 16 volts here, it's 12.8 here, which is on that regulated input. But then my isolated DC to DC supplies turns that into about a 16 volt output. Okay, next section to the video. I'm going to test a desat signal. This is going to take a couple arms, so I have to reach over here and click F. Actually, luckily, just remembered I have a wireless keyboard. So this is going to be super handy for this. What I have to do is I have to hold down this desat connection, because I actually pulled the collector bolt out. What that's going to do is this is going to continue the circuit so the desat reads and looks correct. I've got my scope set on the right signal there, on the right phaser. Probably won't see that because as soon as I click enter, we'll hear the PWM, and then I'm going to actually take and I'm going to remove this, and it's going to trip desat, and it's going to the Arduino is going to shut everything down, and then the PWM will go away, and then we'll look at that. We'll look at what the Arduino is doing and make sure we see what we want to see. So everything's ready. I'm holding it down with my finger. I'm going to click enter. Unfortunately, this keyboard needs to point at the thing, so I got to move it. So now you can hear the PWM. I can take and I can put this probe there, and I'm seeing the PWM like I like. Now here's what happens when I remove that desat wire that I'm holding. It just disappears. Everything's gone. Everything's shut down. We can double check. You can see that it's held off in a negative like it's supposed to be, and that's just because there's no gate signal going to it anymore. So now we can flip this over carefully here, and we can look in under the Arduino, and we can see that the Arduino is flashing, and it's telling me that phase, if I can get the camera to show it there, so you can see 3 flashes. 1, 2, 3. So that's phase 3. Phase 3 is now shut down, which means it's shut all. It's right now it's holding the reset button down on the brain. So what I can do is I can push this, and it tries to start over, and that allows everything. So I push the reset button on the Arduino. It allows everything to start over. we can try that again if we want, but what I'm going to do is I'm going to disconnect the desat connection from the Arduino. So now this is going to allow the desat to repeat itself, and we'll be able to verify that that part of the circuit works as well. I'll try and set that up there so it's happy. This should work. Should be able to go. Now we should be able to go to PWM again here. A, F. Now you can hear the PWM, and watch what happens when I measure this phase. Look at what it looks like. So that's with the desat connection, like intermittently connecting. So there's disconnected, disconnected, and then I gotta bring that back out. Got into a weird spot on me. Gotta hook up my ground clip again. Go through a couple little notes to make here too. So right there, that's what desat looks like. If you're to freeze that, you can see your 50% duty cycle, but it's 3 desaturation events. And if you're to measure that, I want to go, I like to do manual, and then we'll go x-axis. If we're to measure that, it's about 26 microseconds apart from one desat peak to the next, more or less. 34, it's a little different than I thought it was, but either way, doesn't really matter. I just zoomed in a bit to double check that. So we'll go to the start of one. Basically to the start of the next. So 35 microseconds. I think it used to be 26, but it might be different timing with something I've changed in the last little while. Either way, doesn't matter. Oh, what it is it's actually like 26 microseconds till it's shut off completely or something like that. Yeah, that's the end of the period, and then it has a reset period before it turns back on, so that's what it is. Nonetheless, that's what that looks like. And again, just to repeat, you can see I'm like trying to hold the probe with one hand and push the button down so it comes and goes. My ground clip came undone there. Either way, you get the gist of how that works. From there, 2 things I want to mention. First off, the probes that come with these oscilloscopes, as a rule, they're a cheaper probe. They get the job done, but never try and connect this to something that's powered from the wall, because this ground clip is actually connected to the ground and the actual 110 input, and that actually causes a problem. So I believe I've actually snipped the ground off there for a little bit of a safety thing. But another thing is these ground clips are connected between each trace, each input, so you need to be careful on that. So what there is I don't have them here, I have them at home right now, but there's differential probes that are electrically isolated from ground so that you can hook multiple probes up anywhere you want inside something like this without worrying about it. What it is there's a couple little problems that happens is, first off, if you want to scope, for instance, a high side gate and a low side gate at the same time, and you try and hook these ground clips up on a regular probe like this, you'll actually end up with an issue where you'll cause a pass-through. It'll short out through your oscilloscope. If you have the main battery pack voltage applied, you're now putting like 470 volts through the ground of this, because one side's going to be a floating side, the other side's connected to the battery negative. So that's a pretty big sketchy thing. So if you're going to do anything, just try to use one oscilloscope probe at a time. Make sure your main battery pack's disconnected. If you need to use high voltage, get yourself the proper probes. These are not the proper probes for high voltage. These are only rated for a couple hundred volts or something like that, and be really careful when you're even using them at that. If you have to scope something like 100 or 200 volts with one of these, shut everything off, hook it up, make sure it's secure, put some stress release tape or something to hold this thing so it doesn't wiggle around while you're doing your measurements. Then turn your system on. Make sure your attenuator set to 10 times and all that stuff. So from there, what I do is, when I was doing my double pulse testing, is I use 2 differential probes, and then I use one of these non-differential probes. This one measures current, which is an isolated current measurement from 0 to 10 volts. The other two are rated to take something like 600 volts DC, which is pushing it because at a 470 volt DC input, you do get voltage spikes that could reach that high anyway or higher, so you want to be careful. From there, I think that covers what I wanted to mention with probes. More or less, just you can do the easy check like I did without hooking up your ground, and you check each gate signal, which is these screws right here. That's your gate, if you can see where my probe is. And then the emitter is your reference or your ground for each phase. So what I did like on this first phase was that emitter bolt right here that my finger's touching right now. You can see it right there, my finger's touching that emitter bolt underneath. I actually hook up the ground clip to that, and then that's how that hooks up, just so you have a ground reference. And then you hook your probe up to there. Now the brain is shut off, but you can see that it's holding it negative. If I remove that probe from there, it goes back to a float at 0 volts. But if I touch it back to there, it shows you how it's held with negative 5.6 volts off. The same applies to the high side, or the low side. This side is the low side, the negative side. This side's the high side, the positive side. The same applies. The one that has the jumper wire that you had to make, that's your emitter, that's your ground reference. This other screw down in there in front of my finger, way down on the bottom there, that screw is actually where you're going to hook your probe up to do measurements to make sure the gates are working. So I've just verified all the gates. I think that section's good. I can leave my probe there. I'm actually going to shut my power off from my main battery just while I'm playing around with the rest of the stuff, so I don't have to worry about anything. And then I want to mention the last thing that I've done. I have this Overtech potting gun. This is the gun itself. What this does is lets you use these funny black glue sticks. Those big sticks come in a bag like this. Big bag, like I bought 2.5, I bought 5 kgs of these. They have an expiry date, but really if they stay in the sealed bag, what it is they don't want you to moisture to absorb into them and everything. A day like today where it's raining, you don't want to leave that bag open, absorbing moisture out of there, more or less. So from there, I use that potting gun to do some of this stuff like this. I've potted some of my wires. I put this special plastic isolator that goes between the aluminum and the wire, so between the aluminum housing and the wire. Then I also use some of that potting stuff there to kind of glue them and secure them so they don't wiggle around on each other. You can see I got a bit everywhere there. Another place I've used them is actually, if you remember when I was describing how to drill, I'll pull my light here so you can see it better, how to drill in the end of each IGBT and put your current sensor in there. I've actually got my wires for my current sensor dropped down in there, and then I put some potting compound over top of it. You can even see it down in over there somewhere. Each IGBT has its own temperature sensor. I believe I called that a temperature sensor. I hope I didn't call that a current sensor. Either way, that thing in the middle of the picture there, that's a temperature sensor. And those are the digital temperature sensors that all share one wire. They're pretty cool. You can put 8 on the same set of wires. Like you have positive 5 volts, a negative ground reference, and then one wire for the signals from all 8 goes together. And what it does is the brain can actually decipher between all the current sensor or temperature sensors. Sorry, I can't call them current sensors because that's not what they are. I'm going to turn the brain back on. Oh yeah. Actually, we'll disconnect that for now. I'm going to turn the brain back on for 1 second to do one more test here. Oops. There, get that there. Come back in here. What I want to do is I want to just verify the temperature sensors, make sure all my wires are good. This is in the menus, you set it up, you double check this. I want to click C to verify the temperatures from all of them. And they're all reading 1, 2, 3, 4, 5, 6. So right now I've only got the 6 temperature sensors, 1 on each IGBT, because I have a main inverter temperature sensor and a motor temperature sensor read on my display inside the car, but those really don't go up above like 25-30 degrees Celsius ever, so that's not a big deal. And then the last thing is just to, this tells you right here what I've got them set to. So at 70 degrees Celsius, it starts to pull 20 amps per degree Celsius. So I think that covers everything. I'm going to go ahead and put this the rest of the way together, and from there I should be able to drive it out of here today. So I think I've covered everything I want to talk about. You can see how I use the piece to support for strain relief, holding the 3 phase wires. Got my last DC input wire to hook up. That layout shouldn't be too complicated to duplicate. I guess one thing to point out is my negative bus bar here. It bends down just so that it reaches below the cap and stays tight to the cap, and then drops down on this side. That helps keep noise away from all the circuitry down below. Another thing is you can see where this is my main ribbon cable. It's that isolated shielded ribbon cable. That comes over that way so that it stays away from all the high voltage bus bar on this side. That's the best way I could route it. Nothing here is ideal. This is something I've put together that it works well, makes some amazing power, makes a really fun car, and it's step one in many steps of me building awesome inverters. So hopefully this will help you guys who are building these kits figure out what you want to do to keep it going and everything. A quick overview of all the components. Basically, you have your main battery pack. From there you have a safety disconnect of some sort that you manually disconnect just in case your contactors weld, because contactors do weld. You have a contactor on the positive and the negative side. You have some sort of pre-charge circuit, which my little Arduino here inside this case does the pre-charge, and it reads some of the sensors for my gauges inside the car. From there you're going to have something that takes the main battery voltage, which can vary depending on your charging system, your loads, your windshield wipers, headlights, all that stuff varies. You're going to want to take that, put it into a DC to DC that takes in anything and spits out a regulated 15 volt output. From there you want to have a regulated buck converter, preferably. They're cheap and easy to install. That feeds your 2 wires here to feed your driver board's power, and that's going to be a 12.8 volt regulated output. From there you're going to also, off that DC to DC input that sends out 15 volts, that's going to hook up to the brain. The brain's got 2 regulators on it, one to regulate for 5.4 volts for the brain chip itself, the other one to regulate at 10 volts for the, and that's built into it, that's how I designed it. The 10 volts is for the current sensors, which are these current sensors here. There's 3 of them. And then after the brain board, you're going to have your Arduino for sensing desaturation detection. I didn't put the desat on the same one as this Arduino because I want a dedicated device, or whatever you want to use, whether you use hardware or software or whatever, to watch for desat. I wanted that to be dedicated to desaturation detection and not have any other code in there to make it confusing and cause you an issue down the road. We're always changing the code in this. We're about to add a quarter mile timer, 0 to 60, all that stuff built into my gauges in the car. Last thing I need is one of the bits of that code to interfere with what goes on with the desaturation detection and cause the desaturation detection not to work. And the only way to prove it works is like I did with this wire here that I disconnected, that the one bolt goes through right there. You have to disconnect that and make sure it shuts everything down like I showed you in this video. So make sure, and you need to make sure that you test all outputs. The 3 wires on this side are pretty easy to disconnect. To test the desaturation detection and validate that it works on the low sides, you actually take this bus bar and you remove it. So you can do your PWM test mode before you get all your bus bars installed. And you can either install this bus bar, or you can just hold it on there with your fingers and do your test and then take it off and verify if your desaturation, if your oscilloscope shows desaturation, you'll see it there. And then also do that to verify that the Arduino works. Like I showed you, you can disconnect the Arduino for measuring desaturation, and then that'll let you make it do the reset and the short little pulses like you see in the oscilloscope. you need to test all 6 IGBTs. You need to test every output, because that way you can verify that the desaturation detection is working to the Arduino. You want to test that section, and you want to also test that you see it actually work when you see the oscilloscope. From there, I think that covers everything I really want to mention. I'm sure there'll be lots of questions. I might have to make another video, but for now I'm going to try and put this together and maybe drive it home in the rain later. Here's one last video before I pop the cover on. Basically I got the cap. I always leave that warning there. Check cap voltage. If you ever pull this apart, pull your inverter apart to work on it, make sure that your bleed resistor has actually bled the cap down before you touch anything. So what I do is I take a multimeter and I measure positive and negative, which is to these bolts where my 2 fingers are. One will be positive, one will be negative. This side here is negative, this side down below is positive. So basically I check here wherever. If it's close to 0, like 5 volts or less, then I'm okay to work on it. What I do at that point is I take a wrench. Before, I usually take my, because it's supposed to be bled off, your multimeter is telling you it's bled off, but in case you screwed up, I stand back and I take a wrench and I short it out across there just to verify. I do it with one hand, the other hand is behind my back. That is after you've verified with a multimeter that the voltage is at 0. So I do that, and that verifies that it's shorted out so that there's no energy left in that cap to hurt you. You're better off to blow up the wrench, maybe hurt your hand a little bit because it exploded if your multimeter gave you a wrong reading or you didn't measure properly with the multimeter or whatever the hell happened. Better off to short out with a wrench to save your own life. Nonetheless, cap mounts like that, I have a bolt I made on the back of each side to support it. And with all this bus bar on the front, it's actually really rigid in there. These are my 2 wires that come up through the cover. And then I'm about to pop the cover on, so I just wanted to point that all out. Quick thing to add to the video, every single bolt I have in here has, like this one for instance, has a nylock nut at the back of it, as well as on the bolts I put blue Loctite on it, every single bolt. I use this stuff, but nonetheless, make sure you have Loctite on all the bolts. Nordlock washers, a Nordlock washer system would be ideal. I've got so many bolts in there, that would be a lot of money, and I'm actually working on getting a whole bunch of Nordlocks, but I'm trying to find a good place to order them from. So if any of you guys have a good suggestion for that, that's great. But either way, put some blue Loctite on everything. Doesn't matter with just this little bolt holding the cap here. You want everything to stay tight and secure for 2 main reasons. One, you don't want a bolt bouncing around in there causing a short. That'll be a big explosion. 2, more importantly, well, probably just as important, they're equally important. All these bolts that control, that hold things together to flow current, if that becomes loose, that becomes a hot spot, that'll just vaporize that connection. We're dealing with some serious amperage. Hopefully you guys doing do-it-yourself kits won't run the power I'm running, but do whatever you want, I don't care. I don't suggest going as far as I'm going, but with 800 amps coming through one of these bolts and it gets loose, that thing's gone in like half a second or something. Anyways, make sure you use some Loctite and safety stuff. One more thing with this potting gun, I've actually got it on right now, it's going to warm up a bit. What I'm going to do is, I have a couple little holes here to come through the top cover, and you can see I have a grommet that's kind of chewed up, and then the other one's, if my stupid camera will focus, the other one's missing. You can see it there. Anyways, what I'm going to do is I'm going to shove the wires through and just put a little potting stuff around there to support them so they don't short out in the case cover. I've tried to use grommets and they're failing me. I'll have to make a new system down the road, but for now that potting gun's actually pretty handy for that sort of stuff. If you do it right, you can actually make it so you can remove it again later. And the cool thing is with that too is you can use a little hot air rework station or a heat gun, and you can soften and melt the potting compound so you can actually remove it from stuff if you need to down the road.